So the meeting is being recorded also for the people online, so that you know, like, then we can cut the part of the hands-on and so on. Thank you for joining in this week that we are going to have a lot of fun learning about tools. This workshop has been organized in collaboration between CASTIEL and POP. From CASTIEL, basically Blasta and Sim are helping us, and Brian from POP3 has been, and VI-HPS has been putting this together. So what are we going to see? Oh, lot of stuff. Today we have the welcome and a bit of introduction to what VI-HPS is, what POP CoE is, the methodology. And after the coffee break, we will show you some examples on things that we have done with the tools, so that you get excited on that. And then you can start preparing the codes in Mare Nostrum using the accounts that we will provide you to start testing everything, so that tomorrow when we start testing the tools, you have everything already running. So today will be a bit of setting everything up. Tomorrow will be about tools that provide profiling. So we will have Macao, TALP, and OTF CPT. In the morning, the tutorials, and in the afternoon, we will do the hands-on. On Wednesday, we will start with the tracing tools. We will have the BSC tools that include Extrae and Paraver, and also the Julic tools that include Scorpy, Cube. And in the afternoon and the morning, or again, presentations, and in the afternoon, the hands-on to use these tools on your own codes. On Thursday, we will focus on GPUs, again with the BSC tools and the Julic tools. And in the morning, presentations, and in the afternoon, hands-on. And on Friday, we will explain other tools that we have also in POP that include correctness checks, roofline model, and energy measurements. So, and then we will have also some time to test these tools, and we finish before lunch. So a bit of logistics. You have been given a badge to access the building. This badge, you will need to leave it every afternoon when you leave, and we will give it back to you every morning. So you are not allowed to keep it. The coffee breaks will be in the terrace, so it's at the end of this corridor. And the lunches will be in the foyer in front of the chapel. For lunches, you will need your badge. So don't forget it, because you will need to get out, and you need the badge to get out. And you are not allowed to go alone. So you need to go always with somebody from BSC to there. And the toilets are also in this same corridor before reaching the terrace. Being said this, are there any questions? So then I think it was, now it's Brian, right?
So I should share my screen?
Yeah, I'm trying to stop sharing, but
Maybe when my one starts.
Yes, yes. Okay, that works.
Are you seeing my screen now?
Yes, yes. And we hear you well, so you can start, Brian.
Okay, so I just wanted to start the workshop. This is one of a number of workshops we've done, organized by this organization called the Virtual Institute for High Productivity Supercomputing. There's a list of 18 logos of the organizations involved down at the bottom, which we'll come to later. These workshops and the VI-HPS started 20 years ago, so it's now, we'll have our 20th anniversary this year. It was initially started by the Helmholtz Association in Germany, but since then, funding and support has been voluntary and has brought in many more organizations. We have the common goal of improving the quality and accelerating the development process of application codes running on highly parallel computer systems. We have academic workshops organized at various conferences. We have training workshops such as the one we have now, and various other things that have diminished in importance over the years. It was founded by a couple of organizations in Germany, ourselves at Jülich Supercomputing Center, the local RWTH Aachen University, and colleagues at the Technical University in Dresden. Since then, there's been joined by a number of other partners developing tools and interested in tools around the world. So Barcelona Supercomputing Center was one of the early members. I'm not going to go through the entire list, but Durham University just joined last year. We have a university in the north of Brazil. Ines in Portugal, which is part of POP, joined last year. IT for Innovations joined last year or so. So these are all POP partners who you'll hear more about what they've been doing in the course of the next presentations, as well as other national labs and supercomputing centers around the world. Linaro is a company that develops tools and provides platform-independent tools for parallel systems. So they're also partners, and a number of other universities here as well. So VI-HPS has been an organization which we have used to coordinate our activities. We have a variety of different tools that have been developed, and the ones that we'll focus on in the workshop are on this first slide here. There's many more tools that are developed by the different partners that are listed in our tools guide. This is updated regularly every 6 months or so. So if you go to the website for VI-HPS, you'll find the latest version there, just giving a brief summary of the different tools and what they do and what they support. This is the longer list of tools that sometimes feature in one or the other workshops, but I'm guessing we won't cover most of them in this workshop because we're focusing on the tools of the POP Center of Excellence. But just to give the context, there's a variety of tools employed at different stages in application development. Initially, you're probably mostly involved with using debugging and correctness checking tools. So DDT is a full parallel debugger. There's other tools that provide more limited debugging capability, but can also scale to very large numbers of processes and threads. We'll learn about the Must and Archer tools for correctness checking in the course of the workshop. There's also various profiling tools where Macau will be featured, tools that cover both profiling and tracing, such as Scholastica SCORP, or more completely untracing, such as Paraver Extra E. And all of these tools complement each other and have a role to play at different stages in the application development process. This workshop and other workshops like it are an opportunity to learn about what tools are available, how they can be applied, and how to get the best use of them for your own application development. The tools are able to help you, but they don't do everything for you. So they help you understand how your parallel code executes and can identify when and where it's necessary to investigate and work on correctness and performance issues. So knowing how to use the tools is a beneficial part of the application development process. For that purpose, we've organized a number of these workshops over the years. This is our 48th workshop as it's numbered. We started the workshops again, as I said, almost 20 years ago. We've had workshops around Europe and in other countries outside of Europe, with the goal of giving you an introduction and an overview of the different tools that are available, explaining how they work and can be used individually and how they might be used effectively together, but more specifically, to give you an opportunity to try them out and apply them to your own application codes, get some specific feedback about what you can learn about your own code from the different tools that are available. So that's why when you bring your own application code, the code that you're interested in and familiar with, you get the best results from such a workshop, because we're not working with toy examples or arbitrary examples that may be not so relevant to your own work and interest. So I hope that you've made the most of the opportunity and will use the rest of the week to build and run your own applications and apply your tools, apply our tools to your applications on the Mare Nostrum 5 system. As I said, we've done workshops all around Europe. This is our 4th one in Barcelona. Over the years, we've been able to take these workshops to different computing centers and have people attend them. We'll have workshops coming up later this year. There's one we're planning sometime in the spring in the UK in Durham, and then there'll be another workshop in the summertime, beginning of July. We've planned a workshop in Jülich where there'll be a chance to use the Jupyter system that is in the process of coming online and being more widely available. So look out for these workshops. Maybe you're interested in telling a colleague about them. If you're not ready to attend another workshop yourself, but look at the VI-HPS website and the training page in specific for upcoming events. And if you might be interested in hosting a similar event, then let us know. We're always looking for new opportunities to come to different sites and host and arrange such a workshop. So that was the brief introductory slides that we have for VI-HPS, and now we'll move on and focus more specifically on the Performance Optimization and Productivity Center of Excellence, which is the featured organization and the featured set of tools that we're focusing on for the workshop here. So I will hand over to Marta, I think, at this point.
Yep. Thank you, Brian. So yes, a lot of different institutions organizing this workshop. So now let's talk about POP. POP is a center of excellence for performance optimization and productivity, and the idea is to promote best practices in parallel programming. And we do this by providing free services to users, European users, where we assess the performance of their codes and give suggestions or support to improve the performance and portability of these codes. It's a transversal center of excellence, while the other center of excellence are usually focused on one science. We are transversal on all of them, taking care of the performance of the codes. POP now is in its third phase. So we started in 2015, so 10 years ago. And this project will run until the end of this year, until the end of December 2026. So you are still on time of asking for services to us. We have a variety of partners in the project. The nice thing is that we have excellence in performance analysis, performance tools, and in programming models and practices. So all this team allows us to have a diversity of expertise of the tools, of the codes, of the different topics, and give us the different backgrounds to help everybody. The objectives of POP can be divided in two. So on one hand, we have the services where we assess the performance of the code and we provide the second level services. And on the other hand, we advance on the development of tools and methodology for performance analysis. But instead of seeing the objectives as two different things, we need to think of it as different objectives that fit each other. So we need the tools and methodology to provide our services, and from the feedback of these services, we improve the tools and methodology. And this is a wheel that it keeps moving for the whole duration of the project. So we have everything inside the project. Which kind of services we provide? So we provide, the main service is the parallel application performance assessment, where we assess the performance of the code, doing an initial measurement, and usually we point to the bottlenecks and give hints to the developers on what can be improved so in their code to make it more portable, more performant, more efficient. After this, sometimes we detect that there are some things that can be looked at in more detail. And then it's when we offer the second level service that we have 4 different kinds of second level service. The proof of concept, where we as POP3 do a small changes on the code to showcase or point on the hints that we have provided or suggestions that we have provided to the developer. So we make small changes in the code to prove the improvements that this can lead in the performance of the code. The correctness check is when we detect that there's an issue maybe in the code that it just shows sometimes, or depending on the runtime or library that we are using, then we run the code through this check, and we detect things that sometimes are not evident there. The energy efficiency study is also a study on the energy that the simulation is consuming, and giving hints also on how to improve it. And finally, the advisor study is when it's the user, the one that is taking care of the changes of the code, but accompanied by the experts in POP3. So you will do a change in the code, and then we will assess if it's going into the right direction to achieve the performance and efficiency that we were suggesting in the first level service. So all the services are free and are open to any European user. So the only restriction that we have is that the user that requests the assessment is from an European institution. So who are our target customers? Who are we approaching and offering these services to? Mainly code developers, also users. So even if the code is not yours, you can still ask for an assessment, because sometimes also the changes are either easy to make in the code or are related on the way you are running or the limitations that you have or these kind of things. Also to infrastructure operators, so that we can help them improve the way the applications are running in the site, and also to vendors to provide benchmarking or customer support. So how do you access the POP3 services? It's very easy. We have an online form that you can fill, and when you get this, we get a request. We assign this request to a POP3 expert, and here we start the conversation with you. We will ask where do you want your study to be done. If you have your own machine or your own cluster, or you are concerned about the performance in one of your clusters, then we can do the assessment there. Sometimes some users say, no, I prefer to do it to one of the machines that are available to POP. Then we will run your code in one of the machines, and we will do the assessment there. So if it's the POP expert, the one getting the traces, then the user will need to provide all the information to the POP3 expert on how to run the code, which is the correct setup of everything. So it's very important that the setup that we run to analyze, it's the same one that you are running in production and that you are interested in understanding the performance. Sometimes, if you prefer to do it in your own system, then it's the POP expert that explains how to deploy the tracing tools and how to get the traces. Then it's the user who will obtain these traces and provide it to the POP expert. In any case, it will be the POP expert, the one doing the analysis of those traces and obtaining the information. From that, he or she will provide a report and will make at least one call, ideally more than one, because it's interesting to follow this process continuously. So it's not like we do one thing and analyze it and provide the results at the end. It's nice to do calls in the middle to see that we are really running the case that you are interested, that the things that we are finding make sense with what you thought or not, and why. At the end, we provide this report with a call where we explain our findings. And if it's interesting, because in that call we can also discuss there, the user can ask for a second level service. In that case, they can choose one of the services that I explained before. So these are the services that we provide as POP that any of you can ask for. And next, I'm going to jump and I will explain which are the methodology that we follow so that you understand. Okay, so I think the next topic in the agenda is the methodology, if I'm not mistaken. So as I said, inside POP, we have a common methodology and a set of tools. The idea of this methodology is that it can be used with any of the tools that we have in the project. So I'm going to explain the methodology that we use, because that way you will understand better later on when we explain the tools and the different metrics and steps that we do. So in this presentation, I'm going to present the methodology. The methodology is for performance analysis, and it's agnostic to the tools. But in my presentation, everything that you will see is based on BSC tools. Later on, you will see examples of this methodology applied to different codes with the Julik tools and the BSC tools, so two different presentations so that you can get the feeling. So here is more the theory, and you will see how it's put into practice. Also, in this presentation, I'm going to talk only about MPI applications to simplify, because there's a lot of metrics, and I don't want you to be overwhelmed by it. But the methodology is being extended to cover hybrid models with OpenMP, GPUs, I/O, vectorization. So the methodology is being extended. Now, here I'm going to focus just on MPI, but so that you get the idea of the process of the methodology, of the process of the performance analysis. Okay. So what we consider the process of the performance analysis. We consider the process of the performance analysis. We have one system, we have one code, and one input. And this is what I was saying before. It's very important that these three things are the things that you're using in production. So if you usually run in Mare Nostrum, it's better to do the assessment in Mare Nostrum. So instead of going to a different machine, just or using the code that you are running right now, not the one from 3 years ago, because then we will find something and you will say, I have already fixed this. And the input set that you usually run in production, because if you give me, if you are usually running Earth simulation and you give me an empty box that is doing nothing, it will have nothing to do once it will be able. So these three things are the ones that impact the execution, and from here we obtain traces. Then from these traces we can obtain the performance metrics. These performance metrics, I usually say that they are like when you go to the doctor and you get the blood test, and it gives you the numbers and it says there's a warning here. But the doctor with that warning doesn't know what's wrong with you. So it's just a warning. When we get these indicators from the metrics is when we get the traces and we look into what is going on really. So we really do the diagnosis, looking into the traces in detail. So these are like the different steps, okay? And this is what it allows us to give you the diagnosis of your code. So I say the performance analysis is like a journey with different steps. These are the different steps that we will work together today. And we start by identifying the structure of the code. So why we need this step? The objective of identifying the structure is to understand the general structure of the simulation. If there's an initialization, a phase, an iterative phase, which is the granularity. So this gives us the idea, if the user doesn't have a clear idea, because sometimes the user comes and says, I want you to analyze my initialization because I know I have an issue there. Or I want you to analyze this phase. But if not, if they are open, then this allows us to understand where is more important to focus the analysis on. It may seem easy, but it presents different levels of difficulty, as you will see. So for example, these are two traces. These are parameter traces. In the x-axis, you see the different processes, and in the y-axis, you have the times. The different colors identify different things that we can show. In this case, in the top trace, we are showing the MPI calls, and in the bottom trace, the useful duration. So in the bottom trace, you see color when useful code is being executed. here to identify the structure is quite easy. We see that there's an initialization phase here, and then there's an iterative phase where we have a lot of different iterations that look more or less the same. In this case, well, this is another case. Here it's not so easy because the iterations are not regular, so they are not the same all the time. But we can still say, okay, I see that there are different iterations, that they are not regular, they are not always the same, and then a finalization phase that looks different. And here it's another one where we don't see global synchronizations. We are not able to detect an iterative structure. We can try to zoom in and still, so we see some pattern, but it's not easy to say, okay, these are iterations and I can focus on this one. If we zoom more in, we see that the synchronization only happens at the node level, so it's not really possible to determine the iterations. So now that we have seen, so now we have the global view of the application, and we say, okay, what do I want to analyze? What we call the focus of analysis, the FOA. You will see that we refer to the FOA a lot of times here. It means which part of the code we are going to focus and we are going to obtain the metrics. So we go back to the three traces that I showed before, that we selected detected the structure, and we need to decide which are the FOA for each one. The important thing is that there's not a correct answer to this question, that it depends on which are the interests of the user. So if we are open, we can decide something, we can discuss this with the user, but there's not a single answer, and sometimes from one trace, we can do several analyses with different focus of analysis. So for the first application, that was a very regular one, we could decide to take 3 iterations as the focus of analysis because they are kind of representative of the full execution. So we can say, okay, we focus only on 3 iterations, and this will give us the idea of the whole simulation. For the irregular application that didn't have like the same pattern, then we decided to take all the iterations as the focus of analysis, because cutting one or another will give you a very different information of load balance, for example. So in this case, we had to take the whole execution, just leaving out the finalization. And for the very complex one, this one, we did several studies. We did one study with the whole run, because it was not possible to cut it and get a representative cut of the application. But we also zoomed and did an analysis of a subset of the nodes, so a smaller one to really see the details of that run. Once we have selected the focus of analysis, from now on, we will talk about those pieces of traces. And now I'm going to talk about the efficiency metrics, that is this blood test that I was telling you before. So the efficiency metrics that we use in POP, it's a hierarchical model that you can see here. They are multiplicative metrics. This means that all the parent metrics are the product of their child metrics. And they are represented by a scale of 1 to 100%. We see 2 kinds of metrics: the efficiency metrics that are the green ones, and the scalability metrics that are the blue ones. The difference between these two is that the green metrics are computed based on the current run, and the blue ones, the scalability metrics, are computed compared to a base case. So this means that to compute the blue ones, we always need more than one run, because we have one run that is the base, and then based on that, we compute the scalability metrics. So the efficiency metrics, what they are not is the answer to anything. They are more the thing that is opening the questions of what is going on with the code. They are useful to describe the concepts of parallelism, to give us hints on where to look, to quantify the efficiency loss, And we use it to compare. We can compare different versions, different scales, different codes, or even different applications. So it's a way of comparing things or having the same baseline. Let's see. And now I'm going to explain each one of the metrics. And for each one of the metrics, what I'm going to explain is what it quantifies, how it's computed, and what it means when I see a low value in that metric, which are the next steps that I need to follow to understand what is producing that low value in the metric. So remember, the low value in the metric is not the end, it's just what is telling us where to look. So we need to keep looking in the detailed analysis. How we draw them? We usually draw them in a table like this, where we have in the different rows, we see the different metrics, and in the different columns, we see different runs. In this case, for example, they were runs with different scaling, 48, 96, number of MPI runs. And then we see the different values for each one of the metrics for each run. What do I look for when I see a table like this? The easy part is to look for the low values. This is the first warning that we get. But it's not only that. I also look for trends. So in this case, for example, it's very clear that instructional scalability has a low value, but the serialization efficiency is going down. So what this is telling me? This is telling me that probably in the next scaling step, even if this value was not low, this will be an issue. So the trends are very important, although they are not marked as very low values at first sight. And it's also important to check for high values, because, for example, in this case, computational scalability is going up because the RPC is going up. And why is this important? Because this is hiding another problem. So this is hiding the computational scalability is going up, while I have an instructional scalability that is going down. And at the end, the global efficiency is not as bad as the parallel efficiency because it's being compensated by the computational scalability. So high values are hiding something. And usually when you have values that go up, they won't go up forever, as opposed to the ones that are going down, that they can go down forever. So questions. How can it be that there's a value above 100%? Nobody's worried about that. Everybody's fine with values going above 100%. This happens in the scalability metrics, because as I said, scalability metrics are computed based on a base case. So you see here, the base case I have 100% because we cannot compute anything based on this one, and we compute the other columns based on this one. So this means that the IPC here is better than this one. That's why it's above 100%.
Because there's a pathology in the base case.
You can see it like that. So so if you're seeing something that is going up, if I'm getting an IPC here, why I'm not getting it here? That's right. So usually people is happy with seeing this, but they don't ask themselves that.
I have something.
If I can get it here, why not here? That's yes. Okay, so now let's go to the efficiency metrics. But before going into the efficiency metrics, I need to give you a couple of information on the naming that we use. So if this represents a trace that I was showing you before, where we have the useful is the blue, the red is I'm waiting in a barrier, the pink and white is a send receive, and then the orange is a reduce. We summarize all these in two states. Either I'm useful or I'm not useful, I'm communicating. So we summarize the execution of a process in two states. And based on this is how we compute all the metrics. So here you have the formulas, the compute time of a process, the compute time of the application is summing all the compute times of the different processes, of the different bursts of a process, and then of the different processes of an application. So what's the parallel efficiency? The first, so if you remember, we have the global efficiency that is divided into the parallel efficiency and the computational scalability. The parallel efficiency. What is the parallel efficiency? The parallel efficiency is the amount of time that I'm computing, so that I'm in blue here, divided by the total time that I'm using. So in this case, blue plus red. So this will tell us of all the time that I'm using the resources, the computational resources, how much time I'm using it to do useful work. And this is the parallel efficiency. If we have a low value, it means that we are using more time to parallelize and really to do computation. And where do we look next? We look next to the child metrics, because if you remember, the parallel efficiency have two child metrics, the load balance and the communication efficiency. So now we look to the load balance, and to compute the load balance, what we do is we accumulate all the useful time for each process. So it's like pushing all the way here. And then what is limiting me is the one that is taking more time compared to the other ones. So all this time that is in yellow is being lost because everybody else is waiting for the most loaded process. This is what we count as load balance, which is not the common way of thinking. Because if you are thinking on the iterations, let's say, you can see different patterns of load balance. But in our case, we compute it as the global load balance. So we accumulate this, and it's the most loaded process, the one that is limiting me. So we compute it like this. The sum of all the blues divided by the maximum multiplied by the number of processes. So of all this time, how much time I'm using it to compute useful work. What this metric is telling us? It's telling us that there's a process that is more loaded than the others, and it's the one that is making us lose efficiency. It's important to notice in this metric that it's really the most loaded process, the one that is penalizing this. So look at these two examples where I have one process that has twice the work than the others. And this is giving me, if you do the math, this is giving me a load balance of 0.6, 60%. The same situation, but in the other way, I have one process that has half the work of the others. This gives us a load balance of 0.9. So although the pattern seems to be the same, it's very different, because what I'm counting is all this time that I'm losing because everybody's waiting for this guy. While in this case, we are just losing this time here, so it's much less. What to look next when we see a problem in load imbalance? Well, the load imbalance is that one process is computing more time than the others, and the compute time is defined by three factors: number of instructions, IPC, instructions per cycle, and frequency. So the product of these three is giving us the compute time. So then the only thing that I need to do is to find out which of these three things is giving me the load imbalance. Is because one process has more instructions than the others? Or if they have the same number of instructions, is because one of them is computing them faster? Or is because one of them is running at a lower frequency for some reason? So this will be the three things that I would check and would tell me where this load imbalance is coming from. We continue now with the communication efficiency. So if we computed the load imbalance by accumulating all this time. Now the communication efficiency is the time that I'm losing because the most loaded process is communicating. So it will be accounted this pink thing. So we computed as the ratio between the maximum time and the total time. So this time here that I'm losing because I'm communicating. The communication efficiency can have different interpretations. And in general, it means that the interaction between processes is impacting the performance. What I would look next, ideally, the child metrics. The child metrics of the communication efficiency are serialization and transfer. However, sometimes maybe it's not possible to look into those child metrics, and then we will need to check how many calls, MPI calls are made, or which is the granularity of the computation between them. So they are made very often. How much data is sent, which are the semantics, are there a lot of weightings, chains of messages, for example? So we could check all this to try to understand what is giving this low communication efficiency. But ideally, would be able to compute the serialization and transfer metrics. To compute the transfer efficiency, we need a simulation where we assume that we have an ideal network. We say, what if everything that happened through communication was immediate? So every time I try to communicate, the data is there immediately. So there's no overhead at all in MPI. I would still need to wait for the other process to be ready. So if I'm in a barrier, I will still need to wait for everybody to be there. But once I'm there, there's no overhead at all. This is what we call transfer. In transfer is accounted all the time that it's related to MPI overheads, either software overheads, because I'm preparing the buffer, because I'm gathering all the data there and then sending the message, the latency of the network, the bandwidth of the network. So all the overheads related to MPI. We computed, so we compute the ideal trace. We say, okay, imagine every communication was immediate, and then we get a simulated trace, and we divide the ideal between the real time. And this is the transfer. What tells us a low value in the transfer? It means that we have an issue with the overheads of MPI. And what do we look next? Well, we try to differentiate if the issue is more related to the latency of the network or the bandwidth, where the latency also accounts for all the latency of the MPI library. So if the library as a software, as a new layer of software, needs to prepare things, that's also accounted as latency. For this, we can do simulations. For example, in this case, we do a simulation with a low latency. We also do a simulation of the nominal run, and we see which impacts more the execution. We can check if the execution is more impacted by the latency, by the bandwidth, and this will give us information on what this transfer efficiency is, where is the issue with this efficiency. The next one, and for me, one of the most complex metrics is the serialization efficiency. So we have computed the load balance and the transfer, and then everything else that is left is serialization. So the serialization, if you remember, if in transfer we accounted for all the overheads, in the serialization we are accounting for all the weightings. So every time, so all the time that you were waiting for somebody else is serialization, except if you were waiting for the loaded process, because that's load balance. And why it's the most complex one? It's the most complex one because it can have a lot of different sources. So the serialization can be a real chain of dependencies when you have one process and then another one and then another one. What in our mind is more serialization, but it can also be different load imbalances. The example that I was showing you at the beginning, where you have one iteration with one load imbalance pattern and another iteration with another load imbalance pattern, that will be accounted as serialization too. So what to look next? So we need to discard noise. There's sometimes that there's noise in the system, noise in the traces. We need to discard noise because noise also has usually an impact in serialization. We try to identify if there are circular waits, what I was saying, that one process is waiting for another and this one is waiting for another, and you really have a serialization. And try to understand the semantics of the communication. Who is waiting for who that is producing these waitings that we are seeing as the serialization. But for me, it's when you see a low value in the serialization, is one of the most difficult ones to find the causes, because there's a lot of them that can be there. So we finished with the efficiency metrics, and now we go to the scalability metrics. And if you remember at the beginning that I said, okay, now let's divide the processes in two states. The useful, which is the blue, and the not useful, that is the red. Everything that I have said about the efficiency metrics that we have seen up to now were referring to the distribution of this red, where this red was and how was impacting the efficiency. Now in the computing scalability, we are counting the blue ones, how these blue parts, boxes, are being scaled when I change the run. So as I said, we take into account the three main components: the number of instructions, the IPC, and the frequency. So the instruction scalability is how the number of instructions change with reference to the base case. And it tells us if it's a strong scaling, if the number of instructions increased when I divide it among more processes. It can also be computed with reference with a weak scaling case also. Usually, this means that I have code that is being replicated when I'm scaling the code. So that's where I would need to look where these additional instructions are going. The IPC scalability, the same way, but in reverse. Because the higher the IPC, the better. So we computed the other way, and it's again the same. The IPC scalability tells us how the IPC scales or changes when I change the scale or the fold or the input. We would. In this case, if you are scaling, well, it's telling you that maybe you have contention in some resources or a problem with some shared resources. And finally, the frequency scalability is the same case. So we compute it based on the base case. And we need to be careful with this one because it could be noise, preemptions, or changes in the power management of the node. So the important thing is for each one of the metrics to understand what is causing that. And from that detailed analysis is when we can give the conclusions and suggestions to the user, saying, so you have the load imbalance issue here that is being caused by the number of instructions that you are giving to each one of the processes, for example. Also, it's important to notice that these are factors and there are causes. So one cause can affect several metrics. So that's why it's important to do then the detailed analysis, because it's not a one-to-one that the efficiency metric is giving us as an answer. And to finish with, I'm gonna share here the proposal for the GPU metrics that we have, because we will see also the GPU examples in 2 days. So we are proposing to extend the POP metrics to also cover GPUs. To do this, we divide the trees in two. We have the tree of the host, so how the CPU is being used, and the tree for the device, how the device GPU is being used. The host is the same as before, but now we add the host parallel efficiency that is composed by two components, the MPI parallel efficiency, that is the one that I shared, and the device offload efficiency that accounts for how much time the host is idle because it's waiting for the device. And then in the device side, we would have something similar to what we had here, computation and parallel efficiency. So we have the computation scaling of the device and the parallel efficiency of the device. The parallel efficiency of the device will tell us how much time I'm doing useful work in the device, and the computation scalability will tell us how well I'm using the resources of the device. These ones that are in gray are still being defined. So what we have defined so far are the red ones. So this was just a sneak peek, because we will see also in some of the examples the GPU metrics, so that you know where they are. And that was all for the methodology and metrics. Do we have questions? You need a host. You cannot go.
Yeah, but CPU is also on a host, but different like parts and server.
But a device, to run a GPU, you need a CPU.
Yeah.
So that's why we had like the two chips. And then the other main difference is how the GPU is being used. Because for CPU, we didn't go that much in detail on the different parts of the CPU. We just say, okay, they are executing instructions and at one IPC. But then as GPUs have all this more complex hardware, we are trying to understand. This is not defined yet. So this is something that we are looking into that.
But modern CPUs also have like different types of cores and subsets in there as well, right?
Yeah. Yeah, that's something that we are seeing also to see if we incorporate to the vectorization, so how the different units are being used. So, but there's a trade-off between making it general and covering, because of course then you depend on the hardware that you're running. So we want to keep the methodology quite agnostic from the hardware, but then you want to capture these details of the hardware too. Okay, more questions? No? Now comes the exam. Okay. So Brian, do you want to start with the Julik tools example?
Okay. So now is an opportunity to go into a couple of example assessments which have been done with the different tools and give you a bit of a flavor for how the assessments are done and what they show. I need to say a little bit about the tools that we're using. You've seen examples from the BSC tools already, from the Julik tools, Scalaska, ScoreP, Cube. They're similar, but a little bit different. So Scalaska is the main tool for the tool set that does the trace-based analysis, supporting MPI OpenMP in particular. It's open source, but it's using measurements, traces, which are coming from ScoreP. So ScoreP is our instrumentation and measurement infrastructure. that supports two different modes of operation, a profiling mode, a summarization mode, where the data is in a format we refer to as cube. And then there's the event-based tracing, where the data is in OTF2 format. So the tracing and the profiling can be used together, or they can be used separately. SCORE-P supports a range of different parallel paradigms. MPI is the main one for multi-process interoperation. On the thread level, there's OpenMP, or it can be POSIX threads. And then increasingly, we see accelerators being used through proprietary interfaces like CUDA and HIP, or OpenACC, OpenCL, or COCOS. So SCORE-P is the measurement infrastructure. It works as part of the Scholastica toolset because it is responsible for instrumenting applications, instrumenting the source code, linking in additional libraries, producing an instrumented executable, which is then, when it executes, running multiple processes and threads, which is where measurement is done. Those measurements are stored in buffers and within each process and thread. And then at the end of execution, there is a summary report in this cube format, which is a portable format that shows a number of different metrics that have been calculated for different parts of the application program as they're run on with different processes and threads. That summary report can be analyzed and can be optimized, can be sent back for optimization to decide I want more information about one part or less information about another. We can add hardware counters to the measurements. We can augment it in various ways to get a more detailed summary report, or we can decide that we want to get a complete event trace. And then the event trace is something that the Scholastica trace tools would analyze and produce an augmented report, not just including the times which are measured, but also determining these weight states and additional metrics that can augment the analysis report and are shown in a similar format as before. So this display at the bottom with its 3 panels is what we refer to as Cube. Cube is our analysis report explorer. It's also the tools that read and write these analysis reports. Again, it's open source, and in the course of the next few days, you'll have a chance to try it out and see how information is presented. But I'll come to examples in some of the next slides, which we'll look at in a bit more detail. Increasingly, we have a lot of information to present, and which is possible to dig down and investigate. And so, as Marta has mentioned, there are these efficiency metrics that can be calculated for the entire execution or subsets of the execution. And so that's one of the things that has been added to Cube in some of the latest releases, determining these efficiency metrics and then presenting them in various ways. This was one form. It has evolved. So the current version that you'll be using in the next days is slightly different from this, but it gives you at a glance an overview of the various efficiencies that apply to the different parts of the program execution or the entire execution. So Scholastica has been applied to very large application executions on our Blue Gene system, which we used to have in Jülich with more than 1 million processes and threads, or on the K computer in Japan, which had 600,000 cores and was also able to run very large executions. And so we've made sure that the measurement system and the analysis which is possible from it is done in a highly scalable fashion. And so we can get information about very large numbers of processes and threads and increasingly large numbers of accelerators as well. So just let me start with a couple of examples. I'll start with an MPI one. The application I'll look at is an application called HEMLB. We had analyzed it on various systems, including the Blue Water system, before looking at it on the SuperMUC-NG system. The simulation we were looking at was a simulation of the arterial system within the brain, known as the Circle of Willis. It's a C++ application that was parallelized with MPI, and we ran this for 5,000 time steps. So this was a 500 microsecond simulation of the blood flow in this complex geometry. Running on the SuperMUC-NG system, which has Xeon processors, 24 core processors per node. And we were able to run this application and do measurements of it up to more or less the full size of the system. So of the over 6,000 nodes, we were able to get 300,000 and more processes. The application shown here was able to scale very well. Here we're focusing not on the initialization part where data is read in and distributed. That wasn't scaling very well at all. But once it was actually doing the simulation, we could see that the simulation time was scaling very nicely up until the very largest scales of execution here. So up until 3,000 or 4,000 more processes. That's when the efficiency diminished and the scaling tailed off. So it was an interesting test case for us to understand what was happening that was causing the efficiencies to the execution efficiency to diminish at the very largest scale. So these are the efficiency metrics that Marta was mentioning here for the different configurations from a single node with 24. The smallest configuration was 24 compute nodes, 1,000 or more processes. That was the smallest configuration that would actually run this large simulation because it had to be stored in process memory. And then how it scaled up to the largest configuration with over 6,000 nodes and 300,000 processes. The numbers on the left-hand side here show the smallest configuration where the efficiency was not so bad. Of course, the scaling efficiencies are all set to 1, but the communication efficiency was very good, was almost excellent up until the very largest scales when it started to diminish. So that was very encouraging. Load balance was the main inefficiency, but it wasn't an inefficiency that got significantly worse with scale or significantly better. It actually stayed with ups and downs up till the very largest scale. It was always at about the 80% level. So this was due to the complexity of the geometry, the need to partition it and separate this complex geometry and partition it over different numbers of processes. The partitioning algorithm was complicated, and sometimes it worked a little bit better than others. But load balance was one of the major inefficiencies, not only at the largest scales, but also at the very smallest scales here as well. So it was a constant factor that was limiting the application performance. But what changed at the very largest scales was the computation scaling. So that's where we started getting these red figures coming in here, where the computational scaling had diminished substantially. As Marta said, there's a trade-off here between different metrics. There was one which was improving, one which was diminishing. So IPC, the instructions per cycle, was actually getting much better. The amount of data that each process was working with was getting smaller, was fitting better into cache, and so it could be executed more efficiently. That efficiency was increasing by 30%, whereas the instruction scaling, the amount of work that had to be done on each process, it was degrading badly. So it wasn't just the interior part of the grid that was being calculated, but there was a border region as well. The part that dealt with the interactions with the neighbors was increasing in size. So the surface to volume ratio was diminishing poorly. So at this very largest scale, there was just not enough work left for the processes to be doing. In the internal parts of the grid, they were doing most of the work having to process the border regions, the exterior part, and then communicate these messages to neighbors. So that was how we could explain the degradation of efficiencies as we got to the very largest scale here. In terms of what we were seeing in the analysis reports, mostly they were showing very nice efficiency, but here was an example where we have a report which is saying communication efficiency is very good, but load balance in this case is very poor. It's only 50%. And this isn't one of the largest scales here. This is actually only 13,000 processes. So it was a relatively small configuration, but it was showing a problem with load balance. And as we were able to investigate and look at the different metrics and see where this load balance was coming from, we were able to identify that it wasn't uniform. There was just a selected 1 or 2 processes that were showing degraded performance. They were showing, and if what we were able to look at with the hardware counters, that the execution time was dominated by stalls waiting for memory on 1 or a very few processes. And what was most infuriating was that this process, or the processes that were affected, changed from measurement to measurement, from run to run. Even if we were running on the same partition, the same set of nodes, every time we ran the simulation, it was different processes that were affected. And it turned out this was an artifact, a defect of the memory system, that the way in which the mapping of memory was done to cores through a TLB and through a hash table. It had some cases which it didn't handle well. And if one process ended up taking much longer, in this case, roughly a factor of 2 longer than the others for its memory accesses, of course, the other processes have lots of waiting time when they have nothing to do until that process is ready to exchange its information, its border information, with its neighbors and then with the others in the simulation. So we were able to identify some issues with the hardware as well as with the application's load balance itself. So that's one of the issues. If you have a static load balance, you can become at the mercy of the hardware and how well it handles that effective load balance that you have asked for. That was an MPI only version of the application. Over the subsequent years, there was a GPU version developed where they added in a CUDA interface for offloading some of the computational kernels to NVIDIA GPUs in this case. Again, this was an early execution which was run on Volta GPUs from NVIDIA, so some of the previous generations, so a couple of generations old now. It's a slightly different test case, so a different data set as well, but it's the same application and the same execution profile as before. When we're executing GPUs, the GPU kernels are offloaded and executed asynchronously. So they're not shown as part of the same call tree of the application function programs, the application program functions. But when a kernel is offloaded and executed, it's shown in a separate hierarchy, which is distinguished, and then we can see all of those individually, the time for those individual kernels and which CUDA streams that they're executed on, or they can be aggregated together as they've been done in this case. Here, it was the application was using different CUDA streams for different kernels, particularly those ones related to bringing data and distributing it across the GPUs, as well as the interaction between GPU kernels and the data within the simulation. So that's why the different streams have different utilizations here. Some are being used quite heavily, others not at all. And actually, it varies depending on which process it is. If it's one of the ones at the edges, they have less activity and less interactions than the ones in the internal part of the simulation. So we get different metrics that are calculated for the GPUs, which complement those which were coming from the CPU side of things. In our topological representation, where we look at what all of the processes and all of the GPUs are doing, here we have things sorted so that the first column is showing what the processes are doing. In this case, one process per GPU. They're looking pretty balanced here, but the different streams used by the various GPU kernels vary. Some are executing additional kernels or fewer kernels than others. So there's quite a heterogeneous mix here of how kernels are executed across the different GPUs. Another aspect of imbalance that showed up here was the way in which the memory transfers were done from host to GPU. The processes in the middle of the domain were the ones which were transferring much more data, and therefore having longer times for the data transfers. When we were looking at the MPI file I/O costs here, when it was writing checkpoints, we could see that the cost of the I/O for that by the host process in each case was also something it varied considerably across the different processes at the larger scale. So there are lots of different aspects here of performance that we were able to drill down into and explore, and try and explain why the scaling in this case was less favorable and less good as we would have hoped for. So this is a scaling from a single node with 4 GPUs up to 32 nodes in this case. So here, again, a set of efficiency metrics that are calculated. In this case, I'm just showing you the efficiency metrics calculated for the GPUs, because what the host is doing in this case is not very important. It's providing the data, but it's not holding things back. We see that the GPUs have been given work to do that is scaling pretty well up to the largest configuration here of 128 GPUs. But what is not handled so well is the load balance. The load balance is decreasing quite substantially here. So by the time we're up to 128 GPUs, we have a very substantial load balance between them that has appeared. And there's also quite a variation, quite a degradation of the communication efficiency, the way in which data, the time that it's used for data transfers between the different processes. So here again, we're seeing at a glance how the single node execution, which starts off looking pretty reasonable, actually diminishes rapidly and becomes very, very unsubstantial and very inappropriate. So that's two examples from some time ago. I'm actually going to switch to another presentation to show a more recent measurement that was done. Actually, before there's another slide here, which again is kind of summarizing the execution behavior across in the different node configurations. Here in strong scaling, you would expect the amount of time, the sizes, the heights of these bars should stay roughly constant if it's scaling well. The fact that there's an increase in the size of the bars, especially at the larger scale, means that there's inefficiencies that have come in. The colors here show that the MPI file I/O at the larger scale has become a significant factor that's an inefficiency. Also, the time for MPI communication has grown substantially as well. So those are the two main inefficiencies here on the CPU side that have led to the fact that the GPUs are having to wait. So the GPU is either executing kernels, which is roughly constant, this light green part, or it's having to wait for the additional data, the interaction, the memory transfers with the host side of things, and that's this red outlined part here that has grown in size. Okay, so I'm going to switch from this presentation to, as I said, a more recent one. It's not the Jupyter system which is still coming up into production, but it was an early access partition of it known as JEDI. Here we're looking at an application which is a mixture of MPI, OpenMP, and CUDA. It's an echo application from one of the other centers of excellence. So this is from the Exascale CFD Center of Excellence. Again, a test case was provided. We're looking at not the largest test case, but a kind of moderate size one, which was appropriate for this smaller scale of nodes which we had access. We had 48 compute nodes that we could use on this system, each with Grace-Hopper super chips. So I'm going to skip through some of the background here. We could see that this application wasn't scaling very well, and we wanted to understand why that was the case. We were focused not on the input part of it, but on the time step loop. So identifying our focus of analysis as the time step loop was a starting point. That's where most of the time is spent, and so that is the appropriate part to look at. We also see here in the structure that the OpenMP, which is used in this application, is relatively deep down. It's only used in one part of the time step. It's the solve of the pressure. That's the only part where OpenMP is used, and there were a couple of routines that could be executed in parallel, and so that's where OpenMP, if it's employed, could be used. What's more interesting is that both of those kernels and a number of other parts are using the GPU. And if we, okay, here we're seeing that for each of those kernels, the two threads that are being used, one thread is taking longer than the others because the computation is more complex for it than the other. It's the coarse grid solver takes longer than the Schwarz solver, but they could both be executed in parallel if that was the configuration that was chosen to execute. Within the solver, there's lots of detail that can be dived down into. What was more interesting is that throughout this computation, there's lots of MPI being used. There's reductions, there's gather scatter that is being used at various parts. And then there's lots of CUDA kernels which are being executed in relation to that. So the CUDA kernels are being used by to do different parts of the computation. Some of them are being executed on different streams, so they can be overlapped or executed in parallel on the GPU. Here's a list of the different kernels that we're seeing. It's a compressed list here because the list is actually very long, but we can see at a glance that some of the kernels which are the most expensive are the ones related to the gather scatter. So the collection and distribution of data between kernels, between processes. When we look at the execution timeline, here we're looking at it in Vampire, which is a tool that can be used to look at the execution traces generated by SCORE-P. There's an initialization part at the beginning, which is one-off and where the GPUs are essentially not used. And then there's the solver part, the time step loop, which is where there's multiple time steps, 300 time steps in this case, which is relatively uniform before a short finalization, and that's also where some additional file writing would be done, which is again not something that is so interesting for analysis in this entire execution here. So if we zoom into the time step loop a bit more, we can see the individual, or we can see that there's 300 time steps, which are pretty uniform, although there's also instances where we see occasional disruption, where the processes or one of the processes is stalled before it can continue. But basically, the execution is very homogeneous here. And if we do at a single time step, we can see how that time step executes different solvers as part of different phases. So there's a pressure residual solver, pressure solver, velocity residual, velocity solve, all different parts. They're all executing kernels, so the different streams that we're looking at here, each line, the top line in each case is the CPU. The two lines below that are the two GPU streams. We see very little overlap between the GPU streams here. So there's, in this case, no real benefit from using two streams as opposed to one, but we can see that there are kernels executed throughout this solver step. But most of the kernel executions, in fact, all of the kernel executions are relatively short and small. The other thing to notice, but perhaps more difficult to see, is that there's regular exchanges of messages and interactions between the processes and threads here. Those are the red marks here. So each of the processes is regularly exchanging information with neighbors, as well as executing kernels on its own dedicated GPU. Here we're seeing the communication in a bit more detail. We're seeing that there's reductions where all the processes synchronize, as well as these other gather-scatter operations, which are collecting and distributing data between the different threads, the different processes. As I said, the application can execute with two threads because there are two parts to the solver. Those two threads are only ever used within the pressure solve. So we only see on the right-hand side two different streams being used, sorry, two different threads being used. Whereas when we execute with one thread, we have the pressure solve taking longer, but it's doing the two different parts, the Schwarz and the coarse grid. Whereas when they're executed with two threads, those can be executed concurrently. The Schwarz solver is faster, it finishes earlier, and then there's a synchronization where it waits for the other solver, the coarse grid solver, to complete before the routine can complete and continue. Interesting to note here is that both of the threads are offloading kernels to different CUDA streams here. There's also both threads here using MPI operations, so they're both doing communication. So that is one of the explanations for why, although the execution time is faster when both of these are executed concurrently, it's not a complete win here, because as soon as you have two processes here, they're both contending for the GPU when you're offloading kernels, and they're contending for the network interfaces when sending messages. So that contention there means that there's less than a perfect gain from overlap of these two different parts of the pressure solve here. The other thing that became clear was that the overall execution rarely benefited very much at all, because most of the code is executed only by a single thread, and that thread executes less efficiently when some of the data has been sent to and executed from another thread here. So although there was a slight gain in performance for the pressure solve itself, the parts of the code outside of the pressure solve actually executed marginally slower. And so overall, there was very little benefit from, in this case, exploiting two cores using two threads, as opposed to executing everything with just a single thread per process. That's just going into more detail of what's happening on the different threads. At a higher level, summarizing what's going on there, we're seeing the execution and the use of the different CUDA streams, the different CUDA devices by the different processes here. In this case, executing with 32 nodes, 128 GPUs in total. If we want to get an overview of what 128 GPUs are doing, we can use the more topological presentation, where we can see the value for each stream for each one is color coded. Here, everything is very well load balanced. Some of the streams, stream 7 here, which is the one used for data transfers, we don't see any time for, but the ones which are executing kernels we see are very well balanced here. But using a newer version of the cube display, we were able to calculate the efficiency metrics and get a concise summary of the execution, not for the entire execution, but for the time step loop and its associated kernels here. So here, running on 4 nodes, 16 GPUs, the efficiency is relatively good. The load balance is almost perfect, and the communication efficiency is 0.7. It's not so bad. Once we go up to 32 nodes, the load balance has stayed at 0.99, so the load balance is still extremely good, but the communication efficiency, having to do more communications between the host and the device here with smaller kernels, is resulting in a lower overall GPU communication efficiency. As Marta was saying, we can calculate the metrics for the GPU, which are the ones on the top here. or the metrics can be calculated for the CPU. In this case, the metrics for the CPU show that it's not being used very well. It's mostly just waiting for the GPU kernels to be executed and to be completed. Whereas the efficiency for the GPU kernels is also something we see diminishing. Not the load balance. The load balance stays extremely good, but the way in which kernels are offloaded to the GPU, the additional cost of the memory transfers, those result in the parallel execution diminishing quite significantly and not being able to exploit larger numbers of GPUs. So that's a recent assessment which we've done. It was done on a pre-production system. We're now in the process of repeating it on the Jupyter system, where we hope to be able to analyze a larger test case and hopefully see better scalability, but it shows that we're able to calculate and show the information for different applications, different programming models for GPUs as well as CPUs, and present everything not only in a concise overview like the efficiency model, but also go into a lot of detail about what's happening on the different processes, threads, and kernels themselves. So with that, I will hand over to, I think is it Valentin who's going to present the parts with the BSC tools assessments?
Yes.
So let me share my screen real quick. Yes. More. Can anybody? I hope I'm audible in the Zoom meeting. Hi, I'm Valentin. I work with Marta, and I will present you a quick overview for the coffee break of what you can do with the BSC tools and what are the BSC tools. I will not go into detail about everything, but just to give you a rough overview of what you can do. So what we will cover is mainly the ecosystem of our BSC tools, which consists of TALP, which is a profiler that we're developing. We have Extrai, which is basically the package or the trace generation package, which provides you with a Paravert file, and then Paravert, the flexible trace viewer. And then I will apply this to one analysis only, but I will go relatively in depth about this one. So let's start first with TALP. TALP is Catalan for mole, which has the same connotation of being a spy in your application and trying to report back your resource usage to you. How does it work? Well, it basically is a profiler that collects the POP efficiency metrics and provides them to you at the end of the execution. You can tell it, hey, I want also hardware counters. Give me the CUDA, MPI, HIP efficiency metrics. You can query that at runtime as well. So you can also make your application react to parallel efficiency changes, for example. And we have an API to annotate code regions. So if you only want parallel efficiency, for example, for the time stepping, you can annotate your code regions for that. Then one of the most important tools in the BSC tool system is Extrai, because it basically provides all the information that you will analyze. It's basically a tracer. It means extracting in Spanish. So Extrai again is the tracer compared to SCORP in the ULIC toolset. It supports a bunch of programming models. These are not all. These are just I would say the most used ones. It provides hardware counters through PAPI. You can easily link to source through, for example, getting call stacks and the API routines, getting the OpenMP outlier function, so seeing in which function the OpenMP region was. Or you can use DNNs to basically instrument selected user functions. You can also do sampling if you want a more granular view of your application. And of course, there's an API to put your own events in. And all of this without the need to compile or relink or anything. We just interposition ourselves in your application, and you can just use it. Then the tool that enables most of the analysis is para ver, so in Spanish, to see, para ver, which is our flexible trace viewer that we use to visualize the data. And I will explain a bit more about this because you will see a lot of traces and a lot of histograms in the following presentation, so you should be well equipped to know how to handle them. Basically, it's a kind of domain-specific language for any timestamp data. That's a very broad conception. In reality, it's mostly used for performance analysis. It's very flexible. So there's no pre-assumed semantics. So whatever you want to visualize, you can visualize in para ver. It's fully programmable through those configurations, and you will at some point start writing your own configurations and share them with people. And basically, para ver is made up of two kinds of views. Ones are timelines, and the other ones are histograms. Timelines give you a timeline view of your application. Histograms try to reduce it into a statistical view. So I will go quickly into timelines and histograms themselves. We can think of a trace as a function of time and resources, okay? So how do we depict those? Well, we see resources on the y-axis and time on the x-axis. And then we have different methods of displaying that information. For example, for granularity between runtime calls, what we call useful duration, or IPC, network bandwidth, all of these metrics that you measure during your execution, you can display in these gradient colors, okay? So blue in para ver means more, green in para ver means less. In this time, I think it's useful duration, so how long the application runs without calling into a parallel runtime. On the other hand, you can also use labeled data, for example, CUDA kernels you execute, functions that you instrumented within ins or MPI calls. These have like discrete values, so you can use code colors, which you'll also see in the legend, looks a bit different. And you can basically zoom around and navigate your trace with this. Now, if we want to, for example, know how much time do we spend in percentage in MPI broadcast in this application, it's not really obvious, right? What we have therefore is the so-called histograms. Histograms are histograms, so they bin data into bins, basically, okay? So in this case, we bin by MPI call, because this is our semantic information that we display. And we can see for every process on, again, the y-axis, how much time in percentage he spends inside which MPI column, okay? So we have some semantic data that we bin by a semantic range, and that we can display like this. This is very obvious for the code colored versions where we have labeled data. For unlabeled data or more continuous data, like for example, IPC or network bandwidth, it gets a bit more complicated or more abstract. What you basically see is for each resource on the y-axis, you have to think of a bin. For example, this is granularity between runtime calls, and let's say it's between 5 milliseconds here, so 5 and 7 milliseconds gets in this bin, and then we have for 1 second here, and so on. So you basically have the data you're displaying here gets binned here, and then on the y-axis you have again the resources that you're displaying. What we can see here quite nicely is that, for example, different processes take different amounts of time in a certain category of useful duration. You can do this with IPC. You can see a lot of things with this. It's very powerful. Okay. Any questions so far? Good, because now you will see a lot of traces. And anyway, if you have questions, just raise your hand. This is not only a presentation, but can be a bit interactive. So I will mostly be talking about Glasiator, which is Glasiator?
In Catalan?
In Catalan, no. This is a Finnish application, actually. So the people who develop this are from Finland mainly, which basically simulates space weather. So you have an Earth magnetosphere in the Earth, and then we have a solar wind deforming it, and they simulate all the plasma effects that go on in the Earth's magnetosphere. which is quite expensive to resolve because they need to do 60 simulations. So we actually got a very big chunky reset file of nearly 5 terabytes from them that is used to assess this performance. This was of a recent production run, so all you see is actual data from a production run they did. They sent us the restart file from this time step, whatever that means, where the mesh is kind of fully developed, where we have all this dynamic mesh refinement going on and so on. They run at 500 nodes in a Finnish machine. We did those executions here in Estonia, and I will mix and match the data a bit. The conclusions are still valid for all the things I will tell you. So let's look first at the timings, because this is where we normally start, right? So runtime on 250 nodes is roughly 37 seconds for the time step. On 500 nodes is 17 seconds. Super linear speed up. We're done, right? Not quite. We got the chance to scale the application even a bit further onto 1,000 nodes, and there we have a runtime of 18 seconds. So ouch. That's not good. Why? And this is where our parallel efficiency metrics basically give you an explanation. Because at 250 nodes, we only have a parallel efficiency of 50%. At 500 nodes, it's 40%. And at 1,000 nodes, it's only 11%. So we're only using 11% of the available CPU time to do useful computation. Not great. What happened here is, and I don't have a graphics, but basically you scale away in the computation scaling the inefficiencies that you introduce between 250 and 500. And after 500, you could not do any more computation scaling. And then the parallel inefficiency hit you with full blast. How did we go about doing this analysis at this rather big scale? So first of all, I like to have some, so Lazier already had some internal APIs, or FileProf, they call it, internal profiler. We just hooked into that and basically played it back into our tools. Then we gathered metrics for the regions we're interested in with TAL. And then we did a selective tracing of only those regions, because otherwise trace size blows up and so on. And then we basically dig down into the meat of the performance analysis, and this I will show you today. So this is now the overview of the whole application. You can see in the beginning, I hope it's readable, if not, I will point it out. We do some initialization of the grids, then we do a first time step. After the first time step, we try to balance the load a bit. And then we do 3 more time steps. In the end, we do I/O, and then we're done. We will focus basically on one of those time steps, because this is normally what we care about. We don't care about the initialization normally. So propagate is our region time step. So these are the metrics that you just learned about and hopefully perfectly understood. What you see basically is the parallel efficiency is roughly 15%. This is at 250 nodes now. And we can clearly see that MPI parallel efficiency is really low, mainly driven by MPI load balance. Okay, this is the things that TALP gives you. TALP also can differentiate between load balance in one node versus load balance between nodes. And we can see that the load balance is mostly in the nodes compared to between the nodes, which is rather untypical. We can also see that we have a bit of serial code in the OpenMP part of the parallelization. And that's the main information we get from this. But it also gives us a hint where to look. We need to look for MPI load balance and OpenMP serial things. This is now basically one time step of Lazier. On the top, you can see basically what a time step in Lazier is made of, which is the spatial space updates, so X, Y, and Z direction updates, the field solvers, and the velocity space updates. On the bottom, you can see useful duration, which is a very useful view, which basically shows you how much time a process or thread is running without calling any runtime. And the more blue is the longer it's running, so the higher the granularity of computation is. We can, for example, clearly identify a very high granular computation without a lot of MPI calls. You can see very fine granular details here. And we can also see a lot of fine granular things here. Obviously some load balance, and black, by the way, means idle. So for now, we will select 2 focus of analysis, which is basically the first update in the spatial space and the second update or the field solvers in here. First, we will focus on the spatial space. Again, we look at the POP metrics. They're not great. Parallel efficiency is only 11% now because we basically zoomed in a bit, mainly dominated by load balance. So let's try to understand what is happening to load balance. This is now a zoom into only one spatial space update, which is the set direction update of the spatial space. And we can identify basically three phases. First of all, we're going to transfer the stencil data. This is happening here. Okay, all this black region is basically idle CPU because we're transferring to the network. Then we do the actual computation, and then we update our neighbors. Typical code written so by many people. So because we can already see that we have this weird shape here, where the network transfers are happening, let's look a bit into that and see what Paravet can offer us here. So now we're looking at an MPI call view. So basically studying how the MPI calls work in this sub-region, okay? And here we can see that they essentially non-blocking sends and receives. So the I sends, then the I receives, and then wait for them in the MPI wait all calls here. What we also see is the communication matrix, okay? We can see that it seems to be slightly diagonal dominant, so we can see a bit more blue here. But basically, everybody's talking with a lot of people, and we cannot see like a sparse. It's not a very sparse communication matrix, I would say, by any means. In total, this is also maybe interesting. In total, it's a quite big amount of data that is being transferred. So only in the set update, so only updating one direction takes already 6.5 terabytes roughly. So it's moving a lot of data. And we have one process that unfortunately sends roughly 4.5 gigabytes out. Now, what we basically saw in here is that we have this weird shape, right? So some processes take quite long to communicate, these two subsets of processes, and these finish really early. And I wanted to study basically why this is happening. I will explain this in a bit because this is a quite complicated Paravet configuration. But what we're seeing here is, again, this is the 250 node execution that we just saw. What we're seeing here is basically how much data is being sent. So this is the set direction of the histogram in blue or green. Blue means a lot of data is being sent. And then we have the bins of the send bandwidth integral. So at which bandwidth, at which effective bandwidth are the sends happening? And we can basically see 1 gigabyte per second up to 12.5 gigabyte per second here, okay? And we have this peak around 5 gigabyte per second for the 250 node case. What this basically means is that the 250 node case, most of the processes are sending most of the data at only 5 gigabytes per second instead of the expected 12.5, because we have 100 gigabit link in Marinostrum 5. So we would expect to see 12.5 gigabytes per second. We only see these very degraded performance. Now the question is why? Not that easy to figure out. We also did some histograms on message size, and probably what is happening is that the MPI implementation needs to chop up the messages because the message size is just too big in a single message. And that causes these very, very low utilizations of the send bandwidth. For the people who didn't understand the previous graphic, this is the same graphic, just represented a bit differently, because a very nice feature of Paravet is that you can actually export all your data into CSV and just plot it in a different way. Basically the same idea. We can see this is the total bytes sent, okay, by all the nodes. You can see every dot is a node sending of the 250 and 500 nodes. And what we basically see is that we have a rough Gaussian, which is tapered off towards one end, at 12.5 for the 500 node case, where the message sizes got smaller. And in here, we have this weird bimodal thing which corresponds perfectly to these two peaks here as well, at around 4.5 and 5 gigabytes per second. Just telling you, you can export your data and visualize it differently, for example, for publication.
Just obviously, your mesh remain the same for your cases.
Yes, yes. The mesh is the same. Yes. So it's just the message size, the maximum message size that one MPI process sends that causes this slowdown. Looking back, we discussed now this part of the analysis. Okay, so we now know what is happening in the network. Let's have a look at the other part, which is the computation that we're doing. And we will zoom in because with 7,000 processes, we cannot say stuff. So we zoom in into only a subset of the processes. And here I'm looking again at useful duration. Okay. And then what I can do is basically plot how many instructions are in this certain time window here. So I will make a histogram of how many instructions executed by these processes in this time. And what we see is basically that we have this POP process here, these 4 processes. So these are 4 OpenMP threads. We have 6 processes, I think, with their 4 OpenMP threads. We can see that in total, they're doing a lot more instructions. So this is a typical case of load imbalance caused by not properly distributing your work. Very easily visible through this histogram. We can even quantify that. This is 8 divided by 2 is roughly 4x that this process needs to do. Okay, with this out of the way, we can now look at the field solver real quick. We will just zoom into it. You can see that the efficiency metrics look a bit different now, and they're not as bad. But we also see again that we have OpenMP serialization, and load balance seems to be again the problematic one. And this one is a bit tricky. Yeah, this is now the field solvers. Okay, you can see an initialization part of the field solvers and then the iterative part. The OpenMP serialization comes partly from this part. I will not focus on this, but we will only focus on one of the iterations. This is now again one of the iterations of the field solver. What do we see? First of all, we see the slight combing effect in here. Yeah, so I hope you can also see it in the back. You can see that some processes take a lot longer and it seems to be kind of regular. This is the MPI calls. We cannot see anything from that really. At least I cannot. Maybe someone else can. And we can see the internal regions of the internal profiler, where we can see that propagate magnetic field somehow has some longer bursts in here, some longer regions. Okay. Now zooming into the processes even more. So we only want to analyze a subset of processes where we can see more detail. Now we see only maybe 50 processes here with their 4 threads, where you can see basically the structure of the computation. It's a nice image, but we can also see that we have this perturbation going to the right side from this one. Again, MPI calls again, and we can see very high waiting times in the processes that have the perturbation going on. Zooming in into more, we basically now are down to 3 processes. So up here, we basically zoom in here, and we display the parallel functions of OpenMP. So these are now the parallel loops that the compiler has put and that the runtime executes. And we can directly spot the problem. So we zoom again here. We can directly spot the problem. In here, these are only 2 processes. One where everything works fine, and one that is the problem of this whole array of things. We can basically see that these 2 OpenMP loops, the green one and the blue one, they seem to get a lot more work compared to the others. So this is basically an OpenMP load imbalance hidden under a very complicated communication chain, because there's a lot of communication partners waiting here, and also load imbalance in the blue and red one, but at MPI level for the blue and red one, at OpenMP level for the green and blue one. Yeah. So what did we learn? First of all, we learned that Parave is really powerful in exploring traces, so you can basically compute anything you want. We saw an improper bandwidth utilization for the 250 node execution, which contributed to the load balancing we saw. We saw that instructions are the main problem of the computing of the stencil computation. We saw that the field servers have this load balance problems related to instructions in the OpenMP loops, which then causes a cascade of communication delays. Yeah, and that's about it. I hope I didn't run you over, and I hope we got some AC working. Are there any questions so far? No. Then